Today we have two talks. The first one is by Dr. um, the first one is by Dr. Suryadev Pratap Singh. He's a postdoc at Michigan Tech University, doing his experiments with Professor Raymond Shaw in the pi chamber. He completed his BTech in mechanical engineering from Lokanayak Jayaprakash Institute of Technology in Bihar. After that, he moved to IISc to do his master's MTech in Atmospheric Sciences Department, COS. And after that, he did his PhD in Jawaharlal Nehru Center for Advanced Scientific Research, JNCASR, with Professor K.R. Srinivas. And followed by that, he went to Michigan Tech University with Raymond Shaw. He was visiting here for 2 weeks, so it was put up in a very short notice. So thank you, Suryadev, for agreeing. I won't take much time in introducing what he's going to talk about. Probably he will tell us himself, but some very interesting LiDAR measurements in cloud chamber, right? Okay, so I'll hand it over to you, Suryadev.
Thank you, sir. The last. Good afternoon, everyone. So now I will discuss how vertical distribution of aerosol in clouds affect the few atmospheric process and what is its implication in the atmospheric phenomena in modeling. So start with it. So as we all know that clouds are one of the most puzzling part of the weather system and the climate system. And one of the other things that stem from this is the like inhomogeneity in the clouds. Vertical profiling shows that the liquid water content and the ice water contents, they are heterogeneous in the vertical things. And this is from the holographic measurements that has significantly high resolution. You can see that this is scale in the mm. And they can track the droplet positions very nicely and categorize the distribution also. They are highly homogeneous in the scale. So their inhomogeneity scales at the all levels. It leads to a lot of complication in many atmospheric process in the atmosphere. And you can see that this is the image I have taken from flights. Mostly you can see the inhomogeneity at small different patterns.
This vertical profile of this ice is looking at 2 kilometers. From where it is taken?
What?
The vertical profile.
Yes.
Cloud ice.
Yes.
Is 2 kilometers. You have.
Yeah, you can see the temperature.
Any case or any region you have plotted this vertical profile of?
It is this figure from? It's from this paper, is it?
Yeah, this is from one paper. This is not from the pi chambers.
No, I am not talking about pi chamber. I'm just asking that cloud ice is seen at 2 kilometers.
Yes. Yeah.
Just curious.
No, you can see the temperature profile also. They are quite cold at that level also. This is the temperature profile. So ice cloud can exist.
Seen here in tropical regions. That's why from which region? It might be. I have. We should just.
I'm not very sure, but probably from the cold regions. But I'm not very sure. Yeah. So there are many processes occurring at the cloud top. So as like radiative cooling and heatings, as well as evaporation, shear induced mixing, entrainment process and its microphysical response. All this process leads to radiative cooling rate and the evaporative cooling rate. Note that most of the processes are quite limited to 20 meters height of the scale at the stratocumulus clouds, and we will see that the such things where the cloud side distribution play a key role. Another challenge comes in the droplet sedimentation parameterizations. So in the current, most of the weather and the climate models, they assume that all droplets have the same terminal velocity, Hall velocity, which is not true. And they are further complicated by activation, deactivation process in the actual process. depending upon the supersaturation and the environment, and leading to challenge in the sedimentation process. So, because of such challenges, here we highlight that how sedimentation affects the sorting of the droplets depending upon its size, and they are highly evident from the high resolution LIDAR observation in the pi chambers. This is one of the first kind of observation till now. So it comes at the how pi chamber works. So this is one of the facility where we generate clouds sustained for very long time in steady states and get cloud under the control condition, boundary initial and boundary conditions. And principally is relatively simple. We take two air parcels. They are both are moist, saturated enough at two different temperature. And because of the non-linearity in the saturation curve, when we mix, we get super saturations. And when we air the aerosols in the supersaturated environment, we get the cloud formation. So this is a very basic principle, and depending upon the how we inject the aerosols, control the temperature, inject the dry air environments, their properties are quite different. So for this particular set of study, this is the experimental setup where we maintain the warm, humid environment roughly at around 29 degrees Celsius, and top is around 11.5, and the lateral boundary and the center is around 20 degrees Celsius. One important component is the aerosol injection. In this experiment, we vary from the clean condition to very polluted conditions. At the top of the cloud chambers, we have two instruments located. One is the LIDAR, which has very high resolutions and measure the vertical profiles. And one is the glass, which gives direct ground truth by measuring the side distribution and the number concentration, roughly 40 centimeters in the cloud top. So like in visual inspection, it looks streaks, very thin streaks. This particular,
what is the height? I think is 1
this
meter.
is just 1 meter.
1 meter.
Yes, yeah. And resolution is 1.2 centimeter. And this is for the when the clouds are developing, we can see that the LIDAR signals are developing over the time before reaching the steady states condition. So yeah, you can see there are very messy things because this LIDAR is still in developments. We do not have current retrieval algorithm. Still, we are in the developing. So the key point is that their detection time resolution is very high, 40 picoseconds, and the laser pulse with 30 picoseconds, very high short temporal duration from the traditional LIDAR parameters. It leads to very high resolution, going to the 1.2 centimeters in the pi chamber, but it can vary depending upon the requirement. We can configure that things. So based on this, we set up 6 different set of injection for the 6 different set of experiment, going for the 0.27 to 2.65 per centimeter cube per second aerosol injections. It leads to cloud droplet concentration in the pi chamber from 50 to more than 925, to around 925. This considers as a very clean clouds, and this considers very polluted clouds. So idea why to observe all those cases. And as expected, as the cloud droplet number concentration increases or aerosol injection increases, effective radius of the different set of experiment decreases. At the same time, total liquid water content increases. Now comes to the another parameter, that is the backscattering coefficient, volumetric coefficient, and the extinction coefficients. That parameter can be calculated using the Mie scattering theory, using the number concentration, the side distribution, and the parameters which directly relates with the LIDAR equations. So this LIDAR equation is modified and the simple, especially for the pi chambers, and we will use this particular expression to explain all those observed profiles. So first analysis comes that if cloud is homogeneous, what should we expect in the FZ profile? If cloud is homogeneous, we should expect that the FZ or the LIDAR signal should decrease within that cloud. But this is not the case. That is only true in the bottom portion of the chambers. It is not true in the upper portion. Again, I will just point out that at this particular level, we get a notch, and this is because of the injection of the freshly injected aerosols. So we get one that the cloud is homogeneous in the bottom portion, but what happens to the upper portion, we will see. So there are many processes, among that 3 are the most important: turbulent transport, sedimentation, and the entrainment. You will see that the how they play a role. So first thing is the turbulent transport and sedimentation balanced by these, K, the turbulent diffusibility, and this is gradient of the number concentration in the vertical direction and the balance by the sedimentation. When we solve this equation for the upper part of the chamber, considering the velocity measurement of the number concentration, we see that the expected profiles show that particular trend, but they are quite larger. Like here, the dotted line is the observation from the LIDAR, and the solid line is the calculated LIDAR profile based on this mathematical model. So they follow the trend, but they are quite offset. So what is happening at this particular top level? So another process that play a key role, that is the entrainments. So first thing is that we saw in the raw LIDAR measurement that there is a entrainment and detrainment phenomena happening at a different time interval. This can be also observed in one snapshot when the laser sheet is signed and the image taken from a camera. And we can see the entrainment at the cloud top. This is the PIV video. So can you run this video? So this is from the PIV image for the same things. You can see the droplet fields, how the entrainments and detrainments happening at different scale. So obviously this has significant effect on the number concentration very near the top of the cloud because it takes parts in evaporation. Okay, till now there is no very clear physics which explains what is the microphysical response of the entrainment on the cloud property. But another experimental study is done by the Jamie in 2023. They showed that it does not change the radius, but it changes the number concentration, and they are linearly increased towards in the cloud depth. So when we use this particular pattern in the number concentration and further try to model the observed behavior, we see that they are nicely overlapping on each other. Also, we see another thing in that droplet sedimentation happens because of the side sorting. Side sorting means higher the mass, they have higher tendency of settling. So based on that, when we do not account for the side dependent sorting, they are quite offset from the observed one, as like this triangle you can see. But when we consider they are best, when we consider the side dependent sorting, we see that they're very close to the observations. So further, they are also complemented from the ADS study. Note that the entrainment is not accounted in the simulations, but all other aspects are like droplet sedimentation and mean microphysics is accounted, and we say that the radius continuously increases. There are some nodes very near this bottom of the boundary, and this happens mostly because this is the region of very high supersaturation because of the water bed near the bottom panels. And when we take two different levels, we see that the two different level peak of the number concentration at a different level, and when go toward the in cloud depth, this effective radius increases. So that is the observation from the pi chamber, but how it relates to the actual cloud, that is the one very important question. So idea was that how the droplet concentration varies in case of the actual clouds. So we define one parameter chi, that is ratio of the number concentration with respect to the number concentration in the mixed layer of the clouds. So for pi chamber, it can be considered half of the meters leaving from the top and bottom. And for the stratocumulus cloud, mixed layer is roughly 500 meter to 1 kilometers. And we see that what is the height from the cloud top, here the number concentration decreases by the certain fraction. So 90% fraction is one of the we have considered here. And if you just take the side sorting based for the 10 micrometers droplet radius, you see that this is around 10 to the power minus 2 in the scale factor. When we scale it to 1 kilometer scale, it roughly becomes 20 meter. And as we highlighted in the introduction, that 20 meter in the cloud top layer play a key role in the evaporative coolings and the radiative heat transfer and the many other process, entrainment process and other things. And such type of things play a key role, especially in the removal of the liquid water contents, evaporative and radiative cooling. Of course, how the response to the entrainment and the cloud albedo. So such type of mathematical explanation is quite simple, and it can be basis for the developing cloud parameterization in regional and the climate models. So based on that, this is the one of the study. So we see that especially three things: entrainment, sedimentation, and turbulence play a key role in shaping the vertical profiles of the cloud. in which cloud top layer is dominated by the internment effect. After that, sedimentation comes, and the below region is more or less mixed layer when the internment is balanced by the turbulence. So side-dependent sortings and turbulence if the profile above simplified model can be for the basis for improving the vertical parameterization of clouds in climate models. So not only clouds, aerosols also play a key role. This is part of my PhD work, where I have investigated the thermal structure in the atmospheric boundary layers during evening transition and saw how the aerosol play a key role in the radiative cooling. So I will not go into the very detailed radiation modeling, although I have developed in-house, but I will present the key results here. So this is related to sentiment for the Pune and the IITMs as well. You can see this is the measurement happened in the Deccan Gymkhana Hill, Pune, 6 hours on 1931, roughly 1 century back. So this is called the Ramdas layer, first discovered and observed by this particular scientist, one of the great scientists, agriculture scientist. When they observed and they reported involved, no one was accepting because it was against the prevailing wisdom that after evening we expect minimum temperature at the ground, but they observe minimum temperature few decimeters above the ground. So till this time, this phenomena was still not properly understood. They suggested that radiation play a key role, but there is no clear evidence how it plays and how it affects, and no one consider the aerosols. So I work on the radiation models. I simply give the brief history. After the first discovery, Radham Narasimha took this problem to explore the detail and detail. They developed the first version of the radiation model. But because of some erroneous assumption, it did not work out. Radha Punaklakshmi corrected his model, but they did not find the LTM. Further, Mukund done extensive laboratory in the field experiment and highlighted that the aerosol can play a key role. I did a study done by Rafuddin, and I took this problem forward. And so from the field experiment and the numerical solution, one by one, that they are because of the aerosol vertical profiles. So this is my field experiment setup where the lot of high resolution temperature sensor are mounted on the mast, and we observe the LTM for the lot of days, but I considered from the 80 days of the data, very robust data sets. They are the sensor mounting, this wind cube, hat pro, weather station, and the different sensors. I will not go into detail. Basically, LTM appears and sustain over the night, and they disappears when the fog occurs.
Yeah.
Yes.
Where was this setup?
Oh, this is near the Bangalore airport, 150 meters away from the north runway.
Kempegowda International.
Yes, yes, yeah.
This is from K. Srinivasa.
Yes, yeah. So this is the development of the LTM. Every day we see that they start during the evening transition and they maintain, sometimes they disappear and appear. But surprising and interesting thing is that every day, whenever the dense fog appears, the LTM disappears. Basically, the orange dots show the appearance of the LTM when on the long way downward marking lines. So this suggests that radiation play a key role from this evidence. And based on the radiation model, so this is basically three things. One is the observation from the field experiments, this green color lines, and this is for the simulation, blue color with accounting for the aerosols, and again from the same model, simply removing the aerosol, do not account for the aerosol. Surprising thing is that when we account for the aerosols, they are quite close to the observation. Of course, there are some offset, and we expect that the such offset is coming from the advection part, ERA5 analysis data source, but we are not so confident. And we can observe that if you do not account, we have offset of 4 Kelvin, and 4 Kelvin offset is significantly huge, where the 1 Kelvin difference can lead to the fog onset and the fog dissipation. And such type of challenge and the problem in the all models across the weather models, forecasting models, and such high resolution is quite limited in that. So in that context, such type of parameterization needs to improve in all those models, considering the improving the fog forecast and other things. That was not only single problem. In 2010, there was very careful long wave heating rate measurement near the ground. From the, I think, Netherlands, some group, they observed that none of the radiation models able to really replicate this observation. In fact, they are one order of magnitude smaller. So there is no clear reason. There are two landmark paper in which they discussed all those details, but they tried parameterization, forcing something in changing the turbulence parameterization, but nothing worked. So later I took this one and tried to see that is there any role of the aerosols, and we can clearly see that when I account, this is without the aerosols. When I account for the aerosols and see the observation, this is direct from the field observation, calculated from this particular equation. Since we have the temperature profile, so we can calculate the dF by dz. We know the all other parameters. We calculated the radiation divergence and the longitude cooling rate, and we see that the observation are quite close to the aerosol accounted simulation. So this all highlights that the aerosol vertical profiles and the cloud vertical profiles modify the different atmospheric process and needs to be accounted in the weather models as well as the climate models. So I highlight few key points that the LTM, which was first discovered and observed in the Pune, as the origin of the aerosols, and it appears most of the time during evening transition and maintains till fog change the radiative balance near the surface. It play a key role in the thermal boundary layers developments and the LTM. Of course, since it affects the inversion profile and many things, it can affect the fog, pollution dispersion, temperature inversion as well. There are few references, and of course, I would like to thank Professor Raymond Shaw, K.R. Srinivas and his group, Pi Chamber group, all collaborated and the colleagues, of course, IITM and the Professor Vishal Dikshit sir for offering.
Vishal Dikshit is in IIT Bombay.
Okay,
We share the same surname.
Oh, okay.
So, fine, I'll convey your thanks to
Okay. For offering such opportunity. And there are the different agency. This is the Simons Foundation, which has funded for me the postdoc. This is funding for my postdoc work in NSF. And this is for my PhD, Kempegowda International Airport, and the JNC was funded. And this is Pi Chamber Group. And thank you everyone for the listening the talks.
One question.
Yeah.
You were now working on the Pi chamber, and you also worked with the K. Srimas and Arakari sir. So Arakari sir already have a one setup. I don't know, you have seen that Vishak is working in there. So just in that, what is the difference in both the setup?
Okay, so I think we already discussed major, both are the relevant hard convection moist. Major difference is the aspect ratio.
Okay.
Yeah, aspect
The
ratio
diameter is less, you mean?
Yes, diameter is less, and which major implication is that most of the, in case of the tube convection, when the droplet formation occurs, most of the droplets get sedimented on the wall.
Okay.
Not on the surface, but in the Pi chamber, sedimentation happens.
Good answer. Yeah.
Okay. Yeah. So thank you for it, and we are moving into the questions already. Yeah. Gaurav.
Hello, Suryadev. Nice talks. I think I missed the aerosol profiles that you have used in the model that you showed in your I guess last part of the talk.
Yeah, this is the aerosol profile basically that I have considered. So like just a note that aerosol profile is constant profile. It does not change across the days or other thing. And just I would like to highlight that this aerosol data is taken from this particular paper, Hesse et al. OPEC database, because we do not have a direct observation. And we have considered the urban profile because I assume that the runway operation emit a lot of aerosols. And basically I consider these things in property are taken from that particular paper.
And the optical ones?
Optical property is also taken from the OPEC database, Hesse et al. They have extensive data sets.
So do you have aerosol cloud droplet interaction in your model? I mean, formation?
No, I do not have cloud droplet interaction, but I have done some analysis. If it might be here. It is not here, but I can just simply say that what I did that in the later part to observe the effect of the fog, especially because my interest was to study the fog. After the LTM developed, I injected the fog. Like in numerical simulation, after 3 hours of the simulation, suddenly we put a certain vertical profile of the fog, and we see that depending upon where we put the fog, LTM intensity change. If we force the fog very near the ground, the activity participate in the radiation very near the ground, and LTM intensity grow. But when we put at around 90 meter and above that, they really cut off the relative balance and the LTM disappear.
Okay. Okay. Thank you.
Yeah, I think we have a POP group at IITM,
Yeah.
and Gaurav is part of that. So
Okay.
we should talk more to him later. Yeah, Anupam. Yeah. No, Anupam, you continue. I'll give this to you.
Okay. Shiva, nice talk.
Yeah, thank you.
I will come from the last talk and then go back. Yeah.
Okay.
Regarding this fog, you are
Yes.
so which numerical model you are using for this LTM experiment?
Oh, LTM experiments. Okay, this is a numerical model, I can say basically.
Okay.
So this was the first developed by Radham Narasimha group.
Okay.
Ideally, it is from the one of the model developed by NASA group, but Radham Narasimha group took and completely modified because that model failed to work at very high resolution.
Okay. This is a one-dimensional radiation.
Yeah, this is the one-dimensional radiation conduction
Yeah,
model, and my job is to incorporate the aerosols.
Right. Now, I actually echoed with what is mentioning. Basically, the fog forecasting, what you are telling, the model, numerical model failed. But the radiation fog model does not fail at all. This is pretty good.
Yes.
However,
Yes.
the model failed for the additive fog. So additive fog model fails due to the relative humidity biases in the relative humidity. That is where moisture.
Yes.
Actually, go up trying to mention. So what you have mentioned, the model failed the LTM radiation fog. That is not correct.
Okay.
So model is pretty good in forecasting radiated fog very nicely. However, it is not captured particularly dense fog when it is advected fog.
Okay.
That is because of one end is the relative humidity, that is the environment. Second, in the cloud chemistry interaction. So it means the viscosity. So how it activates aerosol. So it importance the activation of aerosol, what we are trying to mention here.
Yes.
So the activation is important, and then rather than aerosol, mixture is important.
Yes.
So that we have shown means high viscosity is important.
So I want to convey the point that like I have studied the Bangalore airport where the offset in the onset time in observation with respect to METAR observation is roughly around 2 hours.
Right.
And we see that there is a significant offset in the temperature profile also.
Right.
So I expect that if we account for such type of things,
Right.
there is a chance that you might reduce the offset in the onset. So this is my major
Exactly. So intensity and direction that
Exactly.
important for you.
Yeah.
Okay. Now your first talk. So I have a couple of questions on this past talk. So what you are talking about the particle parameterization of the cloud. What do you mean in the particle parameterization?
Okay, so especially in the most of the climate models, they take very simplified. First thing in that, if you see here that sedimentation part, especially this sedimentation part, that is poorly parameterized. As far I know, I have not gone in the detail, but from the literature survey,
Yes.
that they consider that all droplets fall from the same terminal velocity.
Yes.
That is not logical, but that is one of the simplified version because of the climate model is already computationally very intensive.
Yes.
But this study highlight basically that when we account for size-based sorting, they can reduce some uncertainty in the cloud top. Yeah.
But when in the conclusion, I'm a little bit confused. That in the conclusion, in your summary or conclusion, you can mention that in the summary. Go to the summary slide.
Yeah.
Yes. The last, the parameterization.
Okay, so basically, what happens that climate models do not resolve the clouds. They take effective size distribution, a number concentration, or mean profiles, and that is quite simplified. But if you see that they should not be simplified in it.
Are you talking about the prediction model?
Climate model.
Okay, so prediction model resolved
the
clouds.
Yeah.
So there is some assumption that's true. So what I guess that you can mention the vertical parameters means vertical calculation of diffraction.
Exactly.
Correct?
Yes.
Okay. So second point is that model particularly cloud environment, the sedimentation of the clouds is not that much important, rather is much dominating over tropical clouds. But in the extreme of this, sedimentation is important. Here,
Yeah.
here it is more important.
Yes.
So because of this lightning or electric field, it impacts on the breakup of the droplets.
Yes.
Okay, so do you have any chance in the pi chamber? Can we get the information of the breakup of the droplets?
No. So currently, I do not think
Right.
that is the
Right.
possibility.
So that only can come from the theory-based parameterization
Yeah,
breakup.
and for that, otherwise, already that is a design process that building the large cloud chamber where we can see the collision and the other process.
Perfect.
But not
My,
now.
my second question, last very important question for the model, because
Yeah.
we have not get more information from the model implication.
Yes.
But I have some idea or queries from here. Can we get the terminal velocity or pulse velocity of the ice crystal from this pi chamber in future?
Yes. In future, you can get because we have some.
Temperature is 22 to 15 degrees centigrade.
Yeah.
15 degrees centigrade.
Yes. But we
can control the minus.
Yes. Yes.
Okay.
Yeah. We can go minus 30, minus 50 till minus 50. They have achieved. So, and we have generated the ice clouds in the system.
So how you can do this ice nucleation in your pi chamber?
So you use separately ice condensation nuclei, not the normal water as like cloud, water cloud type condensation. Here we use NaCl, but there I forgot the exact name, but that is the no, they're not cells. Ice condensation nuclei is something different. They use particular that material.
Okay, so as I wish, I can inject that one.
Yes, yeah.
That can be done.
Yeah.
Okay, so I am just hoping that how much means data you can use for the numerical climate model parameterization. That is because only sedimentation why I got from your model. From your the experiment. Only sedimentation is there.
Yes, yeah.
Okay. Thank you so much. Thank you, Surya.
Yeah, you showed the long wave heating rates.
In second part, I think.
Piles of long wave heating rate computations. So there you use aerosol profile.
This is from the direct measurement.
Direct measurement.
Yeah. So what they did, this is not my. This is from the student. What they did that they calibrated two radiation sensor, putting at the same level for the 3 months.
So it's another plot wherein with aerosols, without aerosols.
This one?
Yeah, right.
Yeah. So okay, so here you can see that this is the basic equations where I assume that there is no reduction, and in this we only parameter that we need the temperature profile. Other things I can calculate.
Yeah, when you include aerosols in model, so you need profile, and also you need whether it's what fraction is absorbing type and single scattering albedo.
Yes. So
all are given.
Yes.
Or you're using some urban model. You were mentioning some urban model.
Yes. Yeah. Opaque database. They are very extensive data sets, and not only that, their daily questions growth has been also considered. That the depending upon the relative humidity change, their size increases, and based on that, their refractive index change, and based on the refractive index, they account for the radiative cooling and other process.
Okay. Thank you.
Thank you.
So maybe if anybody else has any questions, maybe we can discuss after the talk with Suryadev. All right, Suryadev, thank you. Thank you for a nice talk. I think we are on time. Let's move to the next talk today. That is by Professor Kannabiran Seshasayanan from IIT Madras. Can you just check your presentation? Yeah. So Professor Kanna, I met him in a couple of workshops before, and he's visiting Ayuka right now. So I just called him here because he works on very interesting but highly theoretical aspects. So he completed his PhD from ENS Paris in physics, followed by a postdoc in CEA Saclay. And after that, he joined IIT Kharagpur 2020 to 2023 in the Department of Physics. And right now he is in IIT Madras, working as assistant professor in the Department of Applied Mechanics and Biomedical Engineering. So he's going to talk about different regimes. Is it coming up? Okay. Different regimes in rotating turbulent flows. So it's going to be more physicsy talk, as you can imagine. Over to you, Kanna.
Yeah, hello. Yeah, thank you. Thank you for the invitation. So I was just visiting Pune, first time this side of the country, and I was visiting Ayuka, and I thought, why not say hi to Shiv Sai on the way. Okay, okay, let me just quickly check. Yes, that seems to be in order. So I am Kanna, just call me Kanna. I'm part of the Department of Applied Mechanics. I think it should be full screen. Just how do I say Control L. Oh, Control L. Oh no, that's search, right?
No, I guess it's open in browser.
It's open in browser. So how do I screenshot split screen? I'm not familiar with Windows.
Zoom that.
But zoomed out, is it? Okay. I just don't know. I just hope. Yeah. I think this seems more or less fine. I think I can manage with this.
You carry on.
Okay. So yeah, this will give a talk on whatever we do. So do slightly more theoretical work on turbulence modeling in geophysical and astrophysical systems. So what we do is, so we have the GFD lab. So what we do in the GFD lab is to look at different kind of flows. So one set of flows that we are interested in is on dynamo theory. So this is about how planets and stars have magnetic fields. So what governs the existence of magnetic fields in different stars and planets, and what is the amplitude of the magnetic field that one sees in these different stars and planets. Another set of system that we look at is on geophysical flows. Like how do you understand, which most of you are very familiar with, how do you understand flows on top of the ocean, in the atmosphere, and so on. And most of these systems are use, just into like going kind of nowhere.
Let's open it. Adobe PDF नहीं है क्या?
Open करते हैं
Okay, send this computer to me. Hit full screen. You have to live with this.
Oh, is it okay? So I'll just use my mouse probably. Yeah. So it's because this changing the my slightly lower. Yeah. Sorry. Oh yeah, this seems better. Okay. Oh no, even this is.
Maybe I will move the slide.
Okay. Yeah. Okay. So anyway, so I'll just stop here. So basically, we look at geophysical and astrophysical systems, and we use a lot of theory from applied math and statistical physics. We are doing some tabletop experiments. For example, here we show this Faraday instability. So if we take a liquid bath and then you oscillate it vertically, the surface of the liquid builds a spontaneous horizontal symmetry, and it allows for waves that you can see here. And of recent interest is also using some machine learning models to understand multi-scale phenomena. So basically, we try to understand or try to parameterize turbulence models using machine learning kind of techniques. Can you go next slide? So first question is, why do we study rotating turbulence? So the title of the topic is different regimes of rotating turbulence. First question is, why bother with rotating turbulence? Because most of the Earth and planetary and oceanic flows, we are very much in the rotating stratified regime. So what is the necessity to study rotating turbulence? So first point is that it's slightly on the theoretical side, but it's a very nice setup because rotation creates an underlying anisotropy in the system. So basically, usually homogeneous isotropic turbulence, you look at scales which are much smaller than the forcing length scales. You have this universality saying that the small scales obey this Kolmogorov kind of behavior, Kolmogorov scaling. So here, the fact that you have a system which is under rotation, you break the symmetries in the system, and you have a system which is by definition anisotropic. So it's a very good laboratory model to study anisotropic turbulence, right? And second question that is interesting is, does rotating turbulence have some universal behavior? Can we derive something like a Kolmogorov theory for rotating turbulence? And if so, does it have only one single regime or does it have multiple regimes of rotating turbulence? And the final question, that as a turbulence modelist, can we parameterize rotating turbulence? Can we derive effective eddy viscosity models for rotating turbulence? So in this talk, I'll basically review, because it might be slightly on a mathematical side, I'll just basically review recent results, experimental and numerical results, and also talk about some of the work that we did to address these questions. So first thing that you look at when you take rotating turbulence is, what is the governing equation that you look at? So you take the Navier-Stokes equation, you spin the system, and you go into the rotating frame. So this is a Navier-Stokes equation in the rotating frame. And so this is, you have an additional term, which is the Coriolis term. You also have a centrifugal term that you added to the pressure term. So the Coriolis term is basically the source of all the complexities that you see in the system. And to derive these equations, you can always go back to some standard books on GFD. Yeah. Next. So to first, when you get a new system of equations, it's always good to non-dimensionalize, right? So by non-dimensionalizing, you get to know what are the terms that are of importance, right? So if you can try to non-dimensionalize with the typical length scale of an experiment, the typical eddy turnover velocity field, and you also have the time scale from the velocity field, the typical velocity fields in your experiment, and the length scale, and that gives you the non-dimensional Navier-Stokes equation in the rotating frame, which is given by this. So here you can see that the typical time scale of evolution of the velocity field is comparable to the coefficient in front of the nonlinear term. So here the nonlinear term takes importance in this set of equation. Whereas instead of the time scale from the eddy turnover time, you can also look at time scales from the rotation rate, right? So that gives you another set of equation. So it's basically the same equation, but if you non-dimensionalize it, you get a different form. And here you can see that the time scale of evolution of the velocity field is comparable to the Coriolis term. So these two have an order 1 coefficient. So the waves play a more prominent role if you write it this way. Whereas here you're looking at non-linear transfers to play a prominent role, right? So where do you see these effects? So first effect is, let's say you take the just the Navier-Stokes equation, you take the curl of this equation. The first consequence that you see, because you have added rotation as a ingredient into your flow, is the fact that you have this Taylor-Proudman theorem. You take this equation, take Rossby tending to 0. The dominant balance is that partial z of omega 0. So you have vortices which are columnar structures. So we can go to this YouTube channel where they have this nice dye experiment. You see that dyes form columnar structures. There's some numerical simulations of the same thing. You have columnar structures that are being formed. And these are also turbulent structures. You have turbulent columnar structures which are moving around. And yeah, just go on the video. So the other part is, other important aspect of a rotating turbulent flow is the fact that you have inertial waves, right? So what are inertial waves? These are bulk oscillations that are present in a rotating system. So if you excite the fluid at some particular place, you have waves which are being driven. So here you can think of linearizing the equation, and by linearizing the equation, you get this dominant terms in the equation, and you can search for plane wave solutions, right? So these are plane wave solutions, exponential ikx minus omega t, and you can look at what is the frequency wave number relation. So this is called the dispersion relation, right? And how does it depend on the wave number? So this is typically what you see when you look at wave solutions in a particular system. So here what you can see is that for inertial waves, the frequency is independent of the amplitude of the wave number. It's only dependent on the angle between the rotation axis and the wave number, the wave vector, for example. So the wavelength is independent of the frequency. So what sets the wavelength is usually the domain size. So the boundary conditions sets the kind of waves that you see. And what is also interesting is that if you do the analysis, you can show that the root velocity and the phase velocity are normal to each other, right? So if you have so this is an experiment where they show these waves which are being excited. So I mean, I'm not able to play the video here, but if you excite these waves, you have waves which are propagating in this direction, whereas the wave energy is traveling in this particular direction. So the energy of these waves are traveling in the perpendicular direction to the direction of propagation of these waves. So this is an interesting case where the group velocity and phase velocity are perpendicular to each other. And finally, you can see that there's no projection onto the 2D plane. So if the rotation rate and the k vector are perpendicular, sigma goes to 0. So the 2D plane seems to be not affected by inertial waves. Yeah, it's just a wave part. So and you can observe this in the ocean. So if you take the mixed layer on the top of the ocean, you can actually put a probe and measure the fluctuations, and you see a strong peak in the near inertial. So these are near inertial waves, and these are, because not stratified, you can still measure some of these waves that are seen. Right. So another important effect of rotation is also the fact that you get this nice Ekman spiral. So if there's a wind which is blowing, and if your system is under rotation, you have this nice spiral structure that is set up. So this again, you can this is all standard stuff. You can again balance the viscosity and the Coriolis term, and you get this particular structure. Yeah, and it's also very of much importance when you see these Langmuir circulations, where you have the circulations in the mixed layer, the compression. If you have variations of the wind along the horizontal direction, you can have this upwelling and downwelling of flows. Yeah. So let's move on to. So this is the basics of rotating flows. Now let's try to understand. So this is what we've shown is that you have these waves and vortex which are both present. How are they going to interact, right? So can we derive a formalism in which we can understand how they are going to interact? So for that, we take the Navier-Stokes equation, you linearize it, and then you look at normal mode solutions, right? So you can take any velocity field and represent it in terms of normal modes, right? So here you have the velocity field and you have this mode structure. So because the vector field H is the modes that you're looking at, it has a particular structure, and these are the oscillatory part of the wave, and you also have the amplitude part, right? So these are the velocity field. So any velocity field that you have, you can write it in terms of different modes. So these are inertial. It's called the inertial wave basis, and they have some nice properties that you can just derive it. Yeah, and they have some nice helical slightly up. They have a nice helical structure that if you take the curl of that operator, you get this k times that operator, k times the vector. And if you take all the Navier-Stokes equation, you can actually derive the evolution equation of the amplitude, which is given by this equation. It's pretty neat equation, which basically tells you how is the amplitude of a particular mode, how is it interacting with other modes. Right? So this is the it's called a triadic interaction equation if you want, and the interaction coefficients are given by this. And if you do this particular formalism, it obeys all the conservation laws of the Navier-Stokes equation. So you have conservation of energy and conservation of helicity, which are, again, you can show it mathematically, which is not very difficult. Yeah, and one of the main results of rotating turbulence is that the waves can interact with each other in a triadic manner. But when you have 2D modes, vortices, what you can show is that the waves and vortices do not interact. So the coefficient of interaction identically becomes 0. So there's no energy transfer between waves and vortices. So the first question that one can try to ask in a rotating turbulent problem is that how do waves and vortices interact in the first place? Because the interaction, which is basically what the Navier-Stokes equation, because you have the nonlinearity is quadratic. So if you write an energy equation, interaction is always triadic, right? So the first question that you ask in a turbulence problem is that how you have two different modes, you have waves, you have vortices, how are they going to interact? And the triadic way of interaction does not seem to yield any particular energy transfer. So one particular thing that we did was to look at what are known as quartic interactions or quasi-resonant interactions. So instead of just considering triads, you have consider higher order interactions. So you have one triad and interacting with another triad. So this forms what is known as a quartet. Okay. So basically 4 modes which are interacting. And this is a classic study by Valafé in 1999. And we kind of took up some more of this work, and we actually showed that you can actually excite waves and vortices. These two can interact with each other and can lead to energy transfers among the different modes. Next, we'll look at rotating turbulence. Yeah. So the question is, so right now we just looked at the basic formalism of rotating flows. Now, what happens if you have strong nonlinear interactions and you set up turbulence, right? Can you go on? So first question is, how does turbulence affect, how does anisotropy affect turbulence in general, right? So if you have very weakly rotating turbulence, So this is a turbulent simulation in a box, right? If it's slowly spinning, first thing that you can notice is that you have a lot of small scale structures which doesn't have any feature. So they are like randomly oriented, which are interacting with each other. And as you slowly increase the rotation rate, first thing you see is that you start to form a coherent columnar vortex. So this is a co-rotating vortex along, which is pointed along with the direction, which is collinear, or it's in the same direction as the rotation rate. So this is the co-rotating vortex that you see at intermediate rotation rates, and around it you see all the small turbulent structures which are reminiscent of 3D turbulence. And if you keep increasing the rotation rate, we see the strong two columnar vortices which are set up, and you can also see this wave kind of pattern which represents fluctuations of these columnar vortices. So as you increase the rotation rate, the turbulent statistics or turbulent structures themselves changes because of rotation. And one way to analyze this problem is to look at 2D and 3D modes. So 2D modes are basically kz equal to 0 modes. So as I was saying, inertial waves do not project onto the 2D mode. So one way is to look at slow modes. So basically, the turnover time scale is considered to be slow. Another one is to look at fast modes, which are basically inertial waves, basically waves which are oscillating at the frequency of the Coriolis or the rotation rate, right? So we can do this to slow mode and fast mode decomposition and basically look at the turbulence statistics. So one question that it's interested in is, can we parameterize to rotating turbulence? So here I show, we can look at what is known as the dissipation rate, the volumetric dissipation. So you just take the energy equation and you take the term that is responsible for transfer of kinetic energy into much more smaller modes, thermal modes. So that term is given by this epsilon. And we know that if your flow is laminar, this scales like the viscosity times u square over L square. Whereas if it's turbulent, this is called a turbulent drag, or the drag that you see in aeroplanes and all, right? So you have a turbulent drag. So that is given, this term scales like u cube over L, right? So if you can normalize this epsilon with u cube over L, this is what is being plotted as a function of the Reynolds number of the system. So for very low Reynolds number, you have what is known as the laminar scaling, right? So the dissipation rate decreases as the Reynolds number increases. So the viscous term decreases. So you have a decaying dissipation rate, a normalized dissipation rate. Whereas at very low Reynolds number, this transitions to turbulence and it becomes flat. Okay, so there's a transition from laminar scaling to turbulent scaling as we increase the Reynolds number. And now, if you, so this is just the black line represents the classical 3D turbulence picture. Now, if you increase the rotation rate, so the Rossby number is inverse rotation rate. So as you decrease the rotation rate, or as you increase the rotation rate or decrease the Rossby number, you go into more and more of rotating turbulence. And what we see is that if the rotation rates are strong enough, the initial laminar decay continues forward, right? So from a turbulent scaling, you go back to a laminar scaling, which means that the turbulent structures become more and more two-dimensional, and this seems to follow more 2D turbulent kind of picture, right? So you have a nice transition from a turbulent scaling to a laminar scaling as the rotation rate increases. And this was also tested in an experiment where they put a propeller in a rotating tank, and then they asked the question, how much power do you need to rotate the propeller, right? So you can rotate the propeller at a particular frequency omega, and you ask the question, what is the drag? So you put a measurement of the power that is required to drive this particular propeller, and you measure what is the drag that the propeller experiences for different rotation rates. And what they see is that for very low rotation rate or very large Rossby numbers, the dissipation or the power that is required is a constant, which is basically the turbulent scaling. Whereas as you increase the rotation or reduce the Rossby number, you can see that it transitions to a laminar kind of scaling. So experimentally also, you see this transition from turbulent to laminar scaling. And one of the main questions that we look at is, because as you can see that it becomes from 3D to 2D, can it become exactly two-dimensional? So this is a work that was done by my postdoc advisor, for example. So who kind of considered some bounds to show that this particular thing could exist at very, very large rotation rates. And what we did, next slide, is that we actually tried to search if there's such a domain. So if we take the Reynolds and the Rossby number, can we look at regimes where the system goes from 2D turbulence to 3D turbulence, or is there a particularly the threshold, which kind of tells us the boundary which distinguishes pure 2D turbulence to 3D turbulence. So you can do bounds that I just talked about. That's a mathematical technique which tells you there's a threshold somewhere. Or what we can do as in fluid mechanics, what we also learn is to do stability analysis, right? So here it's a transition from one kind of turbulent flow to another. So you're kind of doing a linear stability analysis on a turbulent background. And then you can also ask, if you're doing linear stability, you're actually looking at infinitesimal perturbations. You can also ask the question, what happens if I do finite amplitude perturbations? Do I still get some similar kind of curve? So this is a kind of slightly more theoretical study that we did along with my postdoc advisor and also my students who are working with me currently. So for the linear stability, you can show that there are two basic mechanisms, right? So you can show that there is what is known as a centrifugal instability, and there's a Rayleigh criterion, which basically says that if you have two vortices that are rotating in your box and you have a global rotation, the vortex which is contra-rotating to the global rotation, if you look at particles which are inside that contra-rotating vortex, it's actually spinning due to the vortex itself, and is also spinning due to the global rotation. If these two rates match with each other, so this is the Rayleigh criterion, then the particles no longer feel the effect of any particular rotation and they become unstable. So this is like kind of a hand-wavy argument to talk about the Rayleigh criterion for centrifugal instability. You can do some bounds again and show that this predicts a threshold which is constant. You can also parametrically excite waves because you have underlying turbulent fluctuations. They can also excite waves due to interaction of vortices among themselves, and that can lead to excitation of waves. So these are two different mechanisms, and you can also show that this is has this particular scaling law. Rosby times Reynolds is constant. So we can actually do numerical simulations also, and we actually find these two different scaling laws. So for very, very large Reynolds number and for very low Rosby, you get 2D stable turbulence here and 3D unstable turbulence here. And this domain that you see, the different curves represent different domain sizes, aspect ratios, and you can see that the system transitions from 2D turbulence to 3D depending on this power laws that we just derived. So the theory and numerics seems to agree with each other, and not just you can not only do linear stability analysis, you can also do finite amplitude perturbations. So these are nonlinear simulations. You couple all the modes, and there also you can. So these are the 2D underlying 2D structures, and these are the waves that you see on top of the 2D structures. So it's very interesting that the waves have some localized structures here, and you can show that the threshold that we saw earlier, it still holds, and you have some interesting scaling laws for the energy close to the threshold. Right? These are some recent results that we obtained. So this is just a summary of everything that is occurring. I can just skip that here. So this is if you have waves that are being excited by vortices. So recently there's some experimental results which also look at what happens if you only force waves. So you take a rotating tank, instead of putting a propeller there, you look at a wave. You can generate what is known as waves using a wave maker. So you have plates which are rotating. So you have a time-dependent forcing that you introduce, and then you ask the question, how much? What is the turbulence that is driven by only waves? So this is called it's called weak wave turbulence theory, or the turbulence driven by weakly nonlinear waves, right? And this is a theory that has been derived by Galtier. And this is an experiment in Israel where they took waves which are being generated by, and turbulence which is generated by these interacting waves. And then they asked the question, where is the energy concentrated? And actually, this is a dispersion relation showing the energy content in this particular omega theta phase, where theta is just the angle between the different modes with the rotation vector. And what they showed is that all the energy is on the dispersion curve. So you have very less energy outside the dispersion curve. Most of the energy is on the dispersion curve, which means that energy is mostly due to waves, right? And then there's been more recent experiments where they actually had a bunch of wave makers, and they have a PIV field where the interaction of these waves in the rotating tank led to some turbulence. And if you look at the statistics of these turbulence, it is much different from the statistics that you expect in normal vortex-driven turbulence, right? So you have a slightly different domain of turbulence that is being driven if you have pure waves. Next slide. And also some numerical simulations which basically show the same thing. One important thing that is to be noted is that if you want purely wave-driven turbulence, you need to put some bottom friction. So if you go to the previous slide, actually what you could see is that they had a strong honeycomb grid that they put, which actually damps out the vertical structure. And because there's no vortices which are involved, you only have pure waves which are interacting, and that kind of led to some interesting, that actually led to the theoretical prediction of k to the power minus 5/2, which is the weak wave turbulence theory. If you do not have this honeycomb grid, what happens is that you have a mixture of waves and turbulence vortices, and that gives you a much more complicated theory. You need much more complicated theory to actually understand what is happening. So the numerical simulations show the same thing. If you do not have any friction, large scale friction, or you do not have this honeycomb kind of structure, if you have so this is a simulation in the box, so you can think of a large scale friction term to model this honeycomb structure. What happens is that if you excite waves, these waves interact with each other and actually eventually form a large scale vortex. Right. So in order to avoid forming this large scale vortex, you need to artificially dampen out these large scale vortex modes. So this is what is shown here. So if you have initially, if you're exciting just waves, which is called the non-geostrophic component, after some time it actually excites the vortices, and you have a mixture of these modes. What you can do is to introduce some artificial friction, or the large scale damping term. And if you do that, you can actually damp out all the geostrophic modes, and then you can get energy back onto these dispersion curves that I'm talking about, right? So if you have a system which have both vortex and wave forcing, so these are some more recent results where they actually found that you can have not just columnar vortices, you can also have more complex structures such as vortex crystals or single isolated vortices or 3D turbulence. So you have a zoo of flows which are existing for the same parameter regime, right? So these are more complex systems to look at, right? So with this, all the research that we looked at, we can try to have a parameter space of rotating turbulence. So this is what we attempted early on. So for very low Reynolds number, you have this classical laminar flow, which depends on the Rossby number or not, depending on the underlying laminar flow that you have. And as you increase the Reynolds number, you go into turbulent regime, you get 3D turbulence, or you get different kinds of rotating turbulence. So these are things that we derived and looked at some scaling laws. And actually what we see is that the final state of rotating turbulence strongly depends on how you force the system. So it depends on what is the exact forcing function that you use. And that kind of tells us what is the underlying statistics that you'll observe. So with that, I'll conclude. So what we found is that you have different regimes of rotating turbulent flows, and understanding the parameter space of rotating turbulent flows is actually a challenging problem, right? So you have different kinds of rotating turbulence, and can we try to derive some generic scaling law? And how does it depend on the forcing? So these are still open questions that we are trying to do. And finally, can we parameterize this particular problem? Possibly for rotation driven flows, if you look at dissipation rates, probably there's a way to parameterize it. And this is still an open question that we are looking at. Okay, with that.
Thank you. I think it was a nice but heavy talk, probably for most of us. I have a question, but let's first wait for anybody has a question for. Yeah.
Yeah, so as like increasing the rotation rate, they start organizing into the co-rotating and counter-rotating vertical rods. So what is the ratio between the co-rotating and the...
So this is a classic question called the cyclonic and anticyclonic asymmetry. So this is observed in atmospheres and oceans also. So you have so there's no symmetry. So there's a breaking of symmetry. If you take a pure 2D turbulence, it doesn't prefer the one direction over the other. Whereas in a rotating system, right, you kind of have a preferential rotation in one direction. So it actually depends on the system, depends on the parameters. So this is again the ratio actually depends on the Rossby number. Like how much nonlinear turbulence is it versus what is the rotation rate.
And there is a special distribution of the rods that they prefer to the outer radius region or the near the center.
So that depends on the wall friction. So usually they prefer to be organized in the near the central region. If you have a rotating turbulent tank, you have Ekman layers on the bottom, on the edges also. So you'll have preferential concentration in the inner turbulent region.
Any other questions? Okay, I have a question. So can you go back to that slide of dissipation rate scaling?
The experiment or the numerical simulation?
I think it was both, right?
We had so you had both showing similar kind of scaling.
Not this one. Yeah, this one. So this is so the points there are experiments.
No, these are numerical simulations.
Okay, and the curves are theory.
Curves are just fits.
Fits. Okay.
So basically, these points are the different Reynolds number, and you just look at different Rossby numbers,
right?
And then you extract out what is this dissipation rate,
right? Okay, but these simulations are not. They're what, periodic boxes, right?
So these are periodic box simulations.
Okay, there is no wall involved.
There's no wall involved.
Okay.
If you have wall, then it gets shifted. So that is not yet fully done.
Right. So what it means is if you keep jacking up the Reynolds number for a given Rossby number, eventually you would end up in a regime where
keep Rossby fixed and increasing the
Reynolds number.
We keep Rossby fixed and increasing the Reynolds number. So these curves are not exactly, they have some particular power law dependence.
Right.
So you'll have to follow those curves.
Right. But eventually, I mean, if you want
particularly large Reynolds number, you should go to turbulent regime,
which is constant.
Which is constant. But what we are trying to show later on is that there could be some regimes, intermediate regimes, where it could be more 2D turbulence than 3D turbulence.
Okay.
So it actually depends on the combined parameter Reynolds Rossby relation. It actually sets what is the towards which kind of flow are you in.
Okay. Any other? Oh, okay. Yeah. One.
I'm audible enough.
Yeah.
So you talked about some symmetry breaking, right? So what is the invariant quantity there?
So here I'm talking about. So for this kind of problems, right? So if you can kind of go to the 2D to 3D. So if you just look at this particular problem, so at very rotation rate, the system becomes exactly 2D, right? And the question is, what breaks the vertical symmetry? Right, so Z goes to Z plus delta Z. So if we just move along the Z direction, you have this columnar vortex, right? And what breaks the so what introduces fluctuations of this columnar vortex is a symmetry that is being broken. So instabilities you can think of as breaking some symmetry in the particular underlying problem.
So what is the underlying invariant
Translational invariance? Translational invariance is a symmetry.
So what is the
mirror symmetry? If you want to think of mirror symmetry at Z equal to 0, or just translational invariance, is also a symmetry of the problem. What are the symmetries do you want me to? Oh, you're talking about conserved quantity.
What is the value?
This is just a pure. You can also look at entropy, which is a conserved quantity, and that also loses.
For that actually.
Yeah, that also breaks. I mean, it no longer becomes conserved.
Got it. Thanks.
Yeah, so probably the last question, where can we observe some of these things? Because many of us do here a lot of modeling, observations.
So one place where
RGD simulations. So
this is a very theoretical study. So the idea is that can we try to see such kind of vortices, which are I mean, at least a simple anisotropic system where one can derive some scaling laws. So one place where people actually use such theory is near the poles of Jupiter, where you have strong rotation, which is dominant. And but even then, you might have to add some beta effect and so on. Right? So those are the places that you can think of where you can observe these phenomena. Here is mostly driven by a theoretical framework. Like, can we derive? Can we at least understand the full picture of rotating turbulence?
Right. Okay. If there are no further questions, I think we can thank Professor Kanna for the nice
for the mathy part.
Yeah, thank you. So I thank both the speakers for today's nice talks, and I think this session concludes here. Tea hai na bahar? Yeah, I think there was tea supposed to be arranged. Let's have a look at it. Thank you everyone for attending. Bye.
Did you get the pen? Thanks for the pen.
In the process, actually the problem is academic minutes are not at site. Regarding the not separate, but what you
can I use the slide?
You ask Kaustav, okay, you can start talking to properly. Just make sure that he's allocated.
Anyway, I can.
Regarding Morunima, I had sent you the name of these people who are for this committee for her committee.
That is being done by Medha and Sushmita. I want to. I cannot do everything.
I do understand that.
Because of that, some delay is there. We are on to it. It will come.
Fine, it's fine.
Which is